Welcome back to our course on the fundamentals of nanoelectronics. And this is Unit 2, the introductory lecture. Now, just to remind you what we were doing earlier, we considered this small device and we wrote down the current, the expression for current, and we then linearized it to get an expression for conductance. And the conductance is like this average, this energy average around the chemical potential of the conductance function, which is a function of energy. And what does the conductance function look like? Well, it depends on this density of states and this time that it takes for the electron to get through. And starting from that expression, we obtained this relationship of how the conductivity is related to this ballistic conductance. And that is what we call the new perspective, you see. This new perspective where we write conductivity as ballistic conductance times this mean free path. And we can contrast this with the old perspective, or the one that you have probably seen in freshman physics. Most textbooks would start with something like this, the Drude formula. And here you'll notice the conductivity depends on what you call the free electron density. And in the Unit 1, we talked a little bit about the subtleties involved here. And there's this effective mass, and there's the mean free time. Now, if you compare the two, you'll notice this interesting correspondence, though, that there's these two things here. There's this n over m, which is like independent of scattering processes. It's like electron density, effective mass, things like that. And correspondingly, we have here this ballistic conductance, which is kind of like that. And then there is another term which depends on scattering. This is the mean free time, and that's the mean free path. And the two are related, of course, because mean free path is the distance, average distance an electron travels in a mean free time. So in this new perspective then, this ballistic conductance plays a very important role. And this ballistic conductance, the expression for it, as we discussed, is this density of states times the average velocity divided by the length. And we also showed, or rather wrote it in the form of, in terms of what's called this number of modes. See? And one of the important things we have learned in mesoscopic physics and nanoelectronics is that in really small devices, that m is an integer, so that the ballistic conductance is actually quantized in terms of this conductance quantum, q squared over h. So these are the things that we talked about in the last unit. Now what we want to do in this unit is kind of adopt a specific model for this density of states. As you can see, the density of states plays a very central role in determining how well something conducts. As I said, basically, of course, a material conducts if there is a large density of states around the equilibrium chemical potential, or this Fermi level. But so far we have not talked much about this density of states, right? Where does it come from? How do we model it? And that's kind of the purpose of this unit, is to talk about this energy band models, which give us this density of states, and then try to compare it to the Drude formula and connect it up. Okay? So what's this density of states? Well, I think in Unit 1 I had mentioned that the basic idea is that if you say had a hydrogen atom, then you'll have discrete levels that are spaced by large energies, like the spacing could be few electron volts between energy levels. Now as you get to larger things, then the energy levels get closer together. So you have lots and lots of allowed energy levels. And in some relatively big conductors, where you have hundreds of atoms, it's convenient to talk in terms of what's called the density of states. So this axis is energy, The density of states tells you in a given energy range how many states you have. So it's the number of states per unit energy. Okay. Now, how do you measure this? Well, usually through one way is photoemission experiments. Hit it with light and see how much energy is needed to actually knock an electron out of the solid. So that's how you'd experimentally measure it. Theoretically, how you'd model it? Well, the general models would all start from the Schrödinger equation. You see, something that takes into account the wave nature of electrons. Now, what we'll be doing in this unit, though, is a relatively simple model based on this idea of a energy-momentum relation. So, you see, we have these electrons in a solid, and that's a solid is a fairly complicated object. But one of the very important insights in solid-state physics, an old insight, like backing back from like 1930s, is that electrons in a solid behave almost as if they are in vacuum, but with a different energy-momentum relation or a different mass. And these things we'll talk more about. But the point is that our starting point for this discussion, and that's what we'll take up in the next lecture, is what's called an energy-momentum relation. That electrons in a solid, the energy of electrons in a solid can be plotted as a function of their momentum. And note that this curve might look a little bit like that, but it's really two different curves totally. Because here we are plotting energy versus momentum. Momentum is a vector that can in general point in any direction. Here we have just drawn, say, the momentum in a certain direction, where it can be positive or negative. And the energy is a function of that momentum. Whereas here what we have is energy, and this axis is the density of states, number of states per unit energy, which of course has to be positive. And so there is no negative side to this graph. It's all on this side. And superficially they look kind of similar, but it's very different, you see. And one of our objectives is actually, after we introduce this idea of energy-momentum relation, is to discuss in the next 3 lectures after that, is how to translate that curve into that curve. That is, how to start from an energy-momentum relation and get a density of states or this number of modes out of it. How to do that translation. That's kind of what the next 3 lectures are about. Okay. Now, another thing that we want to do here is connect up to this Drude formula, the one that I mentioned, like what you might call the old perspective. And as I had mentioned in Unit 1, a central difference between the two perspectives here is when you use this Drude formula, the conductivity depends on the electron density. And what's this electron density? Well, the idea is if you have a certain chemical potential that tells you how far the levels are filled, then this N is the number of electrons in that band below it. And we talked about some of the subtleties involved, like what happens when this electrochemical potential is at near the top of the band, for example. But the point is that Drude formula relates conductivity to the electron density, whereas this ballistic conductance, which as we said, plays a central role in our thinking, depends on the density of states or the number of modes, which is only at a given energy. I mean, you have to average it over energy, but at low temperatures, it's just that energy, and at higher temperatures, there's an average involved. Okay? But philosophically, very different things. You see, one is about a value at a certain energy, the other is about this integrated number of electrons. And what we'd like to do in the next couple of lectures here is to connect up those two things. We'll talk about this electron density and why the new perspective that we're talking about usually agrees with what you'd get out of Drude formula also. But then there are times when they may not agree, and of course I'd like to point out that what we are talking about is really much more general. That follows from the general Boltzmann equation. Okay. Now, The next item that we'll talk about after this is a little bit about an actual transistor. That is, as I mentioned before, that one of the things that's driving the microelectronics industry is the ability to make devices smaller and smaller. And the most important device is, of course, this nanotransistor. And a transistor is basically what we have shown here. You know, there's a channel with two contacts. You put a voltage, you get a current. But I've kind of oversimplified, because what we have left out, a very significant thing I've left out, is a third terminal here. Now, this terminal actually is insulated from the channel. So in that sense, ideally, no current should be flowing. Of course, in practice, there are some leakage currents, but the point is, in an ideal transistor, there's no current flowing in this direction. All that this voltage does is to move the energy levels in the channel up and down. That is, you see, you have this chemical potential here, and you have all these energy levels in the channel. If you put a positive voltage, it gets pulled down. And if you put a negative voltage, everything gets pulled up. And since conductivity depends on where the chemical potential is, you see, you can change the conductivity. That is, if you raise it enough, you can stop the current altogether if the chemical potential happens to get into the gap. Because there's two ways of thinking about it. One is chemical potential is fixed, we move the energy levels up and down. Or you could think the energy level is fixed, we move the chemical potential up and down. Right? So, essence of the transistor, of course, is to be able to control how well the channel conducts. That is, control the resistivity. In fact, in a transistor, you're changing that resistivity by several orders of magnitude. And through this gate voltage. So usually you'd have a current versus voltage relation looking something like this for a transistor, where depending on the gate voltage, you see, as you make the gate voltage more and more positive, it will conduct better. So you'll get more and more current. And so far, usually, of course, we have been talking about this low bias regime. That is when you have a relatively low voltage across the entire device. So we are talking about this regime. That's what you call the low bias conductance. And so we have been talking about this dI/dV of around the origin. So what we'll be doing in this last two lectures is, first, in one lecture, we'll talk about how the gate voltage controls this conductance, this low bias conductance, and that will introduce a very important concept of quantum capacitance. And then, in this last one, we'll talk a little bit about the shape of this current voltage characteristic. You'll notice these have this property of what you call saturation. That is, as you increase the voltage, the current wants to get saturated and not increase as fast anymore. And that is a very important characteristic of transistors. That is, ideally, actually, you'd want it to saturate perfectly. But that is proving more and more difficult to do as you go to smaller devices. And that is something we'll talk a little bit about in the last lecture. So that's then broadly what we want to do in this unit. And so we are now ready to move on to the second lecture, starting from this energy momentum relation. Thank you.